So I've been fortunate enough to have spent the last 20-something years working on a pretty broad range of innovative products that have two things in common. I guess the first thing, as you might have just guessed from Paul's introduction, is that they're all Dyson products. So you'll have to forgive me for some fairly blatant product placement going on in this presentation. And the second thing, as Paul also mentioned, is that they all deal in some way with airflow. So I've got a few things to demo to you, and a few, I guess, of the more fundamental principles behind airflow. And hopefully I can draw some thought-provoking analogies on the way that maybe provide some links through to some of the challenges in architecture. So the first problem that we have with airflow is that it's invisible. And that obviously presents some real challenges to us when we're designing products that are trying to kind of maximize the efficiency of that airflow. So the best way to resolve that problem is to put something in the airflow. So I've got my flow generator here, and I can pop something in the airflow, and, oh, that was close. As you might imagine, and just as you would expect, the balls kind of follow that trajectory of the flow until gravity takes over, they drop out of the flow, and then quickly fall to the ground. Great fun in the office, but not a huge amount of learning to be had there. What's a bit more interesting is, I'll turn that flow down, you can find an equilibrium position where, if I'm careful with this, the ball will find the right point, it'll settle down, but again, perhaps not that remarkable. I think most people would imagine that that could happen as long as the flow conditions are smooth enough. What gets a little bit more interesting is if I do this carefully, I should be able to get this to somewhere around about 45 degrees, and that ball is staying in a fairly stable position, wobbling around a little bit. And this is demonstrating a really key principle with flow. And it's actually demonstrating exactly how aircraft fly and how wings work. And that's that the weight of gravity is pulling down on the ball, which is pulling it out of the airflow slightly. I'll just turn that off. And as the ball's dropping out of the airflow, what we're finding is that you end up with the higher speed flow over the top of the ball and atmospheric flow underneath it. And higher speed flow has a lower pressure. So there's a pressure difference between the top and the bottom of the ball, and effectively the ball is being sucked up by that vacuum. And it's exactly what happens on an aircraft wing, where the flow is running over the top of the wing, creating a much lower pressure area, and that's actually lifting the wing up. So it's interesting to think about the fact that usually when you consider an aircraft, I think it's quite natural to assume you've got this high pressure zone underneath the wing that's pushing the aircraft into the air. Actually, it's probably more accurate to think about the opposite of that happening, and you've actually got a lower pressure region over the top of the wing that's sucking the plane up into the air, which is pretty remarkable when you consider something, a big aircraft like an A380 or a 747, just the amount of vacuum pressure that's being applied to that wing to lift an aircraft of that weight into the air. We use this effect on our products. As Paul mentioned, this was a quick clip from one of our early fans. And you can see what's going on here is that the air is exiting through that very small slot towards the rear of that image. But it's entraining a huge amount of air with it. And that's what those blue lines represent. So it's actually pulling the surrounding airflow along with it. And through that, we can get multiplication of the amount of airflow coming out of the product, which I'll come on to a little bit later on. We also see the same thing happening, sorry, I should have skipped on. Yes, with our air wrap hairstyling product, and this shows it really well. So in this circumstance, there's obviously hair in the surrounding airflow that's being entrained in and pulled around the barrel really tightly. I think the next image shows you a bit more clearly what's happening there. And you can see the profile of those surfaces is very much like an aircraft wing, and that's creating a low pressure region which is pulling in the surrounding air and taking the hair with it, which is what causes it to wrap so well around the barrel. So yeah, pretty interesting stuff going on there. But sometimes we also want to take really accurate measurements rather than just looking at the general flow patterns. So in this case, this is our full grid flow rig that's set up in one of our labs in Malmesbury, which is a development rig to give us an idea of exactly how much flow is coming out of a particular product, whether it's a fan or purifier. In this case, it's our latest humidifier product. But the principle's just the same. And you can see there's an array of probes that are hanging off that arm that are sat in the airflow. We take measurements from those probes, and then that arm moves down a couple of millimeters at a time and takes another set of measurements, and it continues on its path until we've covered the whole flow field. As you can imagine, it's a pretty time-consuming test, but what it gives us is a really nice image of what that flow field looks like when you overlay it. So this shows you the shape of the flow coming out of the product. It also shows you, because of those contours, where the peak velocity point is. So we can make some really subtle changes to the shape of that geometry, the critical features around it, and see exactly what the result is on something like this. It's quite interesting to note this was actually from a different product and an earlier iteration, but for this product we were getting 3.39 meters a second. So that peak velocity point right in the middle, that air is traveling at 3.39 meters every second, so pretty quick. But the most remarkable thing is the total flow, which is the other figure, and that's 438 liters. So if you try and imagine what that looks like, it's a big volume of air coming out of that machine every second. And there's only 25 or 30 liters a second being drawn in. So there's a huge amount of amplification going on there just because of that effect, which I demonstrated with the ball. There are some other techniques that we can use as well. This is smoke visualization. So as you can see, it gives a really good indication of what's going on with the air jetting out of those two slots on either side. It's not great for taking measurements, and it's a bit of a messy test, really. It's a lot of work for the technicians to clean the chamber down afterwards, because, as you can imagine, the smoke starts to build up. We need a lot of extraction facilities, so it's great for general observations, but again, not brilliant for taking specific measurements. And there's another method that's very similar. This is a Schlurian mirror. Excuse me for my pronunciation. I think it's a German inventor of it. But this pattern, this shows what's going on if I click back and forward again. This pattern shows us what's going on with temperature differential. So in this case, it's hot air coming out of a hairdryer, and because that's a different density to the surrounding air, we can see by shining a laser through it, we can see what this pattern is. The next image, which you may be fairly familiar with, this is from CFD analysis. So this is computational fluid dynamics, which is a really specialist field of engineering in its own right. Uses some very powerful software programs that allow us to look in detail at some really specific areas of the product. And this is analyzing what happens to the flow inside the air multiplier as it runs around that corner, and we've got to try and get the air around that edge and through to the exit slot. And you'll see that there are 4 very subtly different variations of that, and that's what this tool's really powerful for. So it's not great at giving you absolute values, but it's really good at comparing different designs, so we can do a number of different iterations, analyze them all virtually without actually having to build anything. I guess this is probably a tool that's used more often when we're assessing the effect of wind loading on buildings. We're in the fortunate position with products that are this sort of size. We can use a number of different rapid prototyping methods. We can build many hundreds of these and test them before we actually have to commit to production. I guess you don't quite have that luxury with buildings, do you? But so that's where this tool becomes really powerful to enable us to get a pretty good idea of what's going to happen before we actually commit to building anything. So that's all well and good, but sometimes we want to test and see what's actually happening with the product. And to describe what goes on with the fundamentals of it, I've pulled out some archive footage. Now, this is way before my time. This is back in the 1960s this was done. But this is somebody that was kind of at the forefront of trying to visualize what was happening with flow fields. In this case, it's an electric wire connected to a DC supply. And when you submerge that in water, which I know is a bad thing to do, so I wouldn't recommend doing it, but submerging it in water, you get electrolysis happening. And that releases these tiny hydrogen bubbles, which just so happen to be the right buoyancy to remain in the flow and not get separated out. So it's a really powerful tool that they use to understand what was going on with different flow fields. You can take that piece of wire and you can lie that across the flow, and then if you insulate it at certain points, you then get this really lovely stream of bubbles coming off, which is quite mesmerizing as an image. And this is just the constant release of those bubbles due to that electricity flowing through the wire. Excuse me. So if you take that and then you start turning the supply on and off, you can then get these blocks of bubbles. And when you run that through a pipe, you get some really nice imagery like this. So this is obviously way before there was any CFD packages available. So this is all done with real testing. And what's interesting to see here is that the middle blocks that are flowing through that pipe, they remain pretty much unchanged from the point where they're being released, where that line is on the left, to the point where they exit the pipe. But the blocks on either side, you can see are being kind of, there's something going on and holding them back. And that's the friction with the inside wall of the pipe. And this is a really interesting observation, because if this tells us that's where the losses are coming from, then obviously the internal surfaces of that pipe have a really important part to play. Not just the surface friction, so how smooth that pipe is, but just the amount of it in contact with the flow. Now, I'm sure many of you will remember that if you halve the diameter of a pipe through the constant of pi, you get half the circumference. So there's a pretty linear relationship there. But if you halve the diameter of the pipe, your cross-sectional area goes down by the square of that. So you start to lose your capacity at a much greater rate than your wall section comes down. So the key bit being that if you run this at about 25 liters a second, which is what most of our products sort of run at, that sort of region, you get a huge amount more losses from a pipe that is half the size. So to give it some context, I think we get about 68 pascals of loss, so don't worry too much about the units, through a meter of pipe that's 50 millimeters in diameter. So let's say it's about that big, 50 millish. If you halve that diameter down to 25, you get over 1,000 pascals in loss. So you get something in the region of 30 times the losses just through half the size of the pipe. So that's a really useful bit of information for us. But it's compounded in that when you accelerate the flow, so to try and maintain the same flow rate, so the amount of flow going through a certain pipe, when you make that cross-sectional area smaller, you have to speed that flow up. And you can see that's exactly what's happening here, which exacerbates those losses even more, which is why you get such a massive difference between the two. I think it's quite interesting to know as well from this, there's an analogy that you can draw here with, I guess, people moving through a corridor in a building, particularly in high footfall areas where there's very limited space. I guess you wouldn't expect people to break into a run when they get to a narrowed section, but if you were to consider that accelerated point as being normal walking pace, then the analogy kind of works in that you would imagine people shuffling along before they get to that restriction and then continuing on at normal walking pace. And I think this also highlights the fact that that resistance is all down to the interaction with walls. So anything that's put in place on those walls that will reduce that flow and increase the friction is going to cause a big problem, and particularly when it's a small corridor. So things like bins and fire extinguishers, even signage and doorways, anything that's along those side walls is going to cause a big problem. Less so if you've got a really big corridor, but if it's really small, then that's obviously going to make a big difference. So what we've learned so far is that you want really big pipes. That's great, all well and good, but that's not great when you're trying to design nice, small, light products. I don't really like the word compromise. It's got a bit too much of a negative connotation to it, but I think it's more about trying to find the optimum balance, really, between the key variables that you're trying to achieve with the product. But there are a couple of tricks that you can play. So this is our latest Airblade product, a hand dryer. And you'll see in a second as it shows the particles going through the filter. We've got a HEPA filter in this product, which is an incredibly high efficiency filter. It's 99.95% efficient, 0.3 micron particles. So if you consider a human hair is about in the region of about 70 microns, 0.3 microns gives you an idea of just how small those particles are. Because it's so efficient, the downside of that is that it's quite restrictive. And that's obviously a bad thing for flow. But there's a couple of tricks we can play. So I've made up a duplicate of one of the filters from this product with some paper, which I patiently sat and folded the other night. So if I just take these clips off, this will give you an idea of what you can do. So just by pleating the paper, you can get something that's quite small, and you can get what is around about longer than my arm. So there's 2.2 meters, I think it is, of HEPA media pleated inside the barrel of that filter. What that means is that the air is flowing through that media incredibly slowly. Put it into context, the air that's exiting the blades, as shown in that image there, is coming out at around about 600 kilometers an hour, so pretty damn fast. That very same air has just gone through the filter media, and the face velocity at the filter media is about 0.3 kilometers an hour. So the difference is incredible, and that's really advantageous for us in that it really minimizes the impact of that restriction. So that's all well and good. We've seen that there are some tricks to play. We know that bigger pipes are better, but sooner or later, you kind of have to send that flow around a corner. Now, I'm sure you can imagine that that pipe is pretty much ideal. If you want to send that around a corner, you want a nice big radius, and actually, the bigger the radius, the better. But there's a point of diminishing returns, which is when you get to the point where your radius is about the same as the diameter of the pipe. Once you get beyond that, it's pretty subtle differences. So that's what we try and aim for. You can probably also imagine that that's not great for turning flow around a corner, hard edges. But sometimes we have to make a bit of a compromise, whether that's for manufacturing reasons or anything else. And often we're left with having to decide whether we put a radius on the inside or the outside of that bend. Now, I'm not going to ask for a show of hands, but I think it's interesting to try and work out between the two of them which one's going to be better or not. One of the rules that we follow generally with managing flow is to try and keep the cross-sectional area the same. So as it's moving through different geometries, you want to try and keep that cross-sectional area consistent. And actually, if you consider a ball rolling through A and B, the ball will roll through B exactly as it runs around the corner, whereas A is getting larger and smaller again. The other interesting point to note is that for anybody that's done any plumbing at home, you'll probably recognize that the vast majority of plumbing joints look like B, not A, which is kind of leading on to say that if we consider the losses in a corner being 1, so again, don't worry about the units, but just for reference, if you make that corner sharp, you get 6.5 times pretty much the losses running around that corner. If you put a blend on the outside, that's not really much better. 5.9 times. If you put the blend on the inside, it's 3.5 times. So clearly not as good as the perfect corner, but actually you're getting much greater benefit. The annoying thing is that's the one that's really hard to make. So that's the challenge for us as design engineers, to try and work out how we can make the balance, I suppose, between what's manufacturable and what is the ideal and optimum solution for flow. So we've seen how to manage flow around corners. We've seen what happens when you restrict flow conditions. But what happens when sooner or later you've got to try and expand that flow back out into a bigger space again? Well, this is where it gets really interesting in that there's a strange thing that happens when you expand flow and you go beyond a 7-degree angle, which is the magic number. All CFD engineers will have that in their head. And you get separation of the flow. So what's happening here is that the flow is coming from left to right. The bubbles are being released at that line, but actually half of them are going backwards, back upstream, which is a really strange observation. But it's very repeatable, and in fact, you can, if you disturb that flow and divert it to the other wall, it will quite happily stick to the other wall as well. and you'll get exactly the mirror image of that happening. This kind of helps to visualize the biggest problems that we have with flow, and that's that it tends to want to stick to a surface. And that looks like it's a fairly gentle opening. And when you consider what happens with water flowing around bridge supports, for example, this is exactly what you'd get. Anybody that's been canoeing in a fast-moving river will probably have been in a situation where they're suddenly going past a bridge support, and you find that the boat is being pulled back in towards that support, or it's turning around and around, and that's because you're sat in that kind of turbulent zone at the top where it's returning. And I guess this is where I was going to finish, really, is one of the key lessons to think about, I guess, is that it's not just the positive pressure that creates an issue. And I'm thinking about, obviously, buildings being subjected to huge forces from high wind speeds. But actually, the vacuum that can be generated could be just as problematic as well. And that can occur in areas that you might not expect it to happen in. I think we've probably all seen the accumulation of litter or of leaves in entrance foyers to buildings. And that's exactly because what's happening is what's shown in this image, is that is being recirculated past an abrupt edge. So I think that's a really interesting kind of observation and thing to take forward. That's where I'm going to leave it. Thank you very much.
Thank you very much for that, Ben, and a bit of a magic act there. I think this is a first for WAF. I hope you enjoyed it as much as I did. And it immediately set off thoughts in my mind about the work that you've done on flow being applicable, at least conceptually, to all sorts of situations in buildings, which are not about your product as such, but where the principles of flow really come into play. For example, I was thinking about the dimensions of fire escapes or single stairs where you may have to evacuate people in a hurry. And I suppose that even though you're thinking about primarily about product design, there's presumably quite a wide range of reference in your thinking, or whether you're discussing it, you know, in the office, restaurant, or whatever it might be, about other situations, especially in the built environment, where flow comes into play.
Yeah, that's right. I think it's been really interesting. I've been talking to obviously quite a few CFD engineers. I don't profess to be a CFD engineer at all, but there are a few specialist guys within our business. And it's amazing when you start talking in detail about the behaviors of flow, how well the analogy works with particularly the movement of people through buildings, but also the challenges that faced by architects who are working on buildings that are really subject to high wind speeds. Obviously, the higher up you go, the higher the wind speeds. But the other observation is the interaction between those buildings. I think in really built-up environments, you can end up in situations where you're creating wind speeds that are far, far higher than what's in the background in open spaces. So I guess there's a consideration not only there to the structural integrity of the building itself, but also to the people that are walking around those buildings, and certainly in kind of entrance areas and where those buildings are interacting.
Well, I was remembering the engineer Bill Baker, who worked on the Burj in Dubai, and the structure and the form of that building. The phrase he used to describe what they were doing was kind of duping the wind. So every time that the wind hit the building, it would the wind, as it were, as a person, would find itself slipping away, and whatever it tried to do, it always slipped away because of the way that the facade had been contoured. And this was so fascinating. But is this sort of work about the effect of wind on buildings something which is actually sort of part of your world, or is it just a kind of...
Yeah, I'd like it to be.
Without giving away any trade secrets. But I mean, you know, in a world where towers are increasingly ubiquitous, I mean, it looks like that's an interesting area. Yeah,
it is. Yeah, I must admit I have no idea what architectural marvels are in James's mind to look at next. But yeah, I'm not sure a tower block would fit well in Malmesbury. But yeah, I'm sure it's something that the principles kind of carry over pretty well. So I would be be very interested to see how architects get around the same sort of problems.
Because what struck me was some of the amazing statistics you had about the speed that the air's coming out, because if I got it right, that air in, air out amplification was a sort of order of 10.
It's many more than that. So it was if I remember the numbers correctly, it's 600 kilometers an hour from the hand dryer, from that 9kJ, 600 kilometers an hour and 0.3 going through the filter. But the amplification for the fan, it was over 10 times the amount of air coming out.
Now, I'm assuming that level of efficiency is presumably the argument, about in the world of CO2 emissions, why hand dryers, the case for hand dryers is actually relative to towels and laundries and paper, etc., 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 has something to do with this extraordinary speed with which they work.
That's right, yeah. I mean our efforts are focused very much on making our products as efficient as they possibly can be, and that means reducing its amount of energy usage. I think if you look at the full kind of carbon footprint of a product, for us certainly, the vast majority of that is taken up through the product's energy consumption in use. So if we can reduce that as much as possible, then we can make a massive change to the amount of energy that's being consumed.
And presumably in an engineering sense of doing as much as possible with as little as possible is a kind of holy grail of an idea of perfect efficiency, which in some senses you seem to be approaching in some areas. I'm always interested in where you have, we could call it a problem, or let's say the condition that it's always the surfaces of the flow that are going to be the biggest challenge for you. And in a way, it isn't a problem, is it? It's a condition. A condition is a problem that's always with you. Is there a temptation, or do you get into the science of the manufacturer of those linings themselves? To what extent do your investigations into flow then become investigations of material science and what's happening there?
Yeah, 100%. And actually down to the point where, for those of you that have seen the way injection mold tools work, which is how the majority of plastic components are formed, is you have to have pieces of steel that form the cores, which will create the hole in the pipe in the center. And actually, even looking at exactly how those pieces of steel interact with each other, you can often leave some very fine witness lines or flash lines. So we have to work incredibly hard to make sure that those lines don't exist, and if they're in a particularly sensitive position, they're at a point where they don't trip or disturb that airflow. And it's that level of attention to detail that makes the difference in that when you're searching for that last 5% in efficiency, you have to put an increasing amount of effort in to try and identify those tiny, tiny marginal gains.
I mean, as it were, you don't want the tracks that the bullet leaves from the revolver.
Right.
You want it to be kind of the perfect object.
Everything needs to be smooth and polished if we can. And there are obviously some manufacturing constraints that we have to take into consideration. But we're quite fortunate in that James is very happy for us to invest in very complicated injection mold tooling, so putting a lot of investment in up front, which we get the gains from in the product performance. It makes it very challenging for tool makers and for us as design engineers, but ultimately very rewarding because you've got the maximum amount of performance from that product.
Well, I once, I don't think this is an unfair question, I once asked Johnny Ive from Apple, I said, how many ideas that you haven't put into production, not to say you won't ever, but, have you got, in your back cupboard? And he said, you just wouldn't believe it.
Yeah.
And I think there were drawers full. And presumably sometimes in product development generally, there are ideas that would work, but you'd think that the market isn't ready for them. I mean, there's an interesting, because any manufacturer as opposed to a pure product supplier has to be mindful of a whole different set of circumstances, don't they? And I wonder what the relationship is between the people actually doing the design, and then the brand manager who says, well, actually we can't do that this year. Don't abandon it, but not for the moment.
Yeah.
I mean, I imagine that's a fairly familiar.
It is, and it's an interesting and healthy conflict that we have between the kind of engineering teams and the commercial teams, perhaps. But as a bunch of engineers, we get quite excited when we're given a challenge, and often you become very engrossed in the detail of that and delivering to that particularly challenging spec that you've been set. And sometimes you're not in the best position to assess whether or not it's the right time to be launching that product, or whether it's going to sit well. So we have a separate team that are kind of focused on making sure that we're on the right track, and a pretty robust process for challenging that in the early stages. So we're not committing too much too soon on something that's on shaky ground.
Yeah.
But you're absolutely right that there's projects that we kick off in the early stages and invest a good deal of time and energy into, that you look at and you think, well, there's a 95% chance this is not going to make it, but it's good fun trying, and every now and again something pops through that does make it, and they're the winners.
Now, you having trained as a product designer, joined Dyson, you sort of Dyson man and boy sort of thing, if I can put it like that. And I'm just wondering, because I can't really remember the chronology now, but was there a sort of moment in the company where, the big product was all about sucking dirt in? It was all about suction.
Yeah.
Was there always a feeling, well, actually, we're not in the suction business, we're really in the manipulation of air business? Or was there a moment when psychologically, oh my God, we're flipping, we're not just going to do suction anymore, we're going to do blowing? Or was there more of a sort of,
Yeah, I don't think it was a conscious decision. I think we've always very much supported our engineers going into the labs and building things and trying them out, trying out ideas. And although sometimes it can take a while to get the results you want, it's the learning that happens along the way that is the really valuable stuff. The things that you didn't intend to discover or build, that you identify as a strange phenomenon and you go off and investigate. And that's what can spawn whole new ideas and new products. And I think that's really where it's come from. We were playing around with a completely different product idea and suddenly noticed what was happening as the air was flowing over this edge. And that kind of set us on a path of discovery, which led to air multipliers and fans and purifiers and so on, including air wrap tools and a whole host of other products that I can't talk about. So,
and your latest one that you did show, which is an air blade, this is another hand dryer.
That's right.
And is the advantage of that over the existing in terms of its own efficiency, or is it a different experience? I haven't experienced it.
Yeah, so there's a few things really there. The big one for us is that the efficiency is even higher than we've had before. So we're drying hands with much less energy. The 9 kJ, which is the name of the product, actually refers to the amount of energy that's consumed. So that's really the marker for us. But there's been some other developments as well. One being the format of the product is actually quite a straight line configuration. So the air goes in through the filter, goes straight down into the eye of the motor, and then out through the blade. So we're doing very, very little manipulation of the airflow and trying not to lose energy as we're turning it.
So you put your hands underneath, or do they still go in?
No, so they just sit in front of those posts. And we've actually also introduced a curvature to the blades themselves, which is just through a process of optimization and continuing to tinker with that to see what will maximize the effectiveness of that blade of air stripping the water off your hands.
And how do you do your, I asked this because the chief designer for Grower or for Lixer, we had a good conversation about this, about the human interface between, in their case, shower heads. How how do people really shower?
Yeah.
And
Yeah.
they filmed a lot of people showering,
Yeah.
is how they found it out. Now, presumably, when you've developed a new model like this, I mean, you do experiments with real people to record their experiences, or is that you do it yourselves?
Well, a bit of everything, really. I think there's quite a funny test rig, which is effectively a set of rubber hands, which allows us to do very controlled, repeated measurements, but obviously they don't behave in quite the same way that real hands would. So we then turn to doing a lot of user trialing, and that may be with a select group of people within the business, or we then go externally to kind of validate what we've been doing. But it's interesting to see the amount of variation that you get in the habits of and how people interact with the machine.
Are there differences between men and women?
I haven't interrogated the data to see differences in gender, but certainly there are differences in just the general behavior and how you interact with that product. And it's also, we have some people that are known to be very consistent, so we like to use those people because they help to identify if we made the product slightly better or slightly worse.
Because there's that fascinating thing about the danger of averages, that if you do the thing that looks absolutely right for Mr. or Mrs. Average, it's actually a disaster.
Yeah.
And it's probably a trade secret about how you exactly do that. But I think it's fascinating territory. I think we should probably end it there, but I think it's what I find with these discussions with product designers and products in general is that actually the issues you face and the sort of analysis and approach you bring is remarkably similar to what other professionals are doing in the built environment, particularly on the engineering side. But then there is that moment where actually the human experience and the human interface becomes in its own way critical.
Absolutely.
Ben Morse, thank you very much indeed.
Thank you.